So you don't need to, are you guys ready? Ladies, are we ready? So you don't need to have a new sheet. You can just add it to the notes you took over the weekend. We're just doing 2 more parent graphs with that. So the first one that we're going to look at is cubic. Which is y equals x cubed. And whenever we look at a new parent graph and we're trying to graph it and find different characteristics of the graph, the first thing we want to do is look at the table so that we know what our x and y values are that we're going to work with. So what are the x values that we've always used every time? So it doesn't matter what the graph is, we're always going to use those. So for this one, I'm just going to go ahead and see what my y coordinates would be. I've got -2 to the 3rd power gives me -8. -1 to the 3rd power gives me -1. And then I know that 0 multiplied by itself 3 times is still 0. And then +1 to the 3rd power would be +1, and +2 to the 3rd power would be +8. So we're going to go ahead and draw a little sketch of this so you guys know what the parent graph looks like. So if you want to take your notes on graph paper, you definitely could.
Do we need calculators?
Yes. Let's maybe do that real quick.
That's better. Let me see how
So every single person should be drawing a sketch of the graph. When you look at the points, do you see how they're like almost a straight line, but not quite? Or it seems like the 3 middle points could be, but the 2 points on the ends kind of mess it up. So these graphs kind of look like a parabola if you took one side of it and like bent it down. So, but it's like skinnier than a parabola would be. So the right side curves up, and then the left side curves down. Like that. So they're definitely not straight. People call cubic graphs S-curves sometimes. Doesn't quite look like an S, but that's what they call them. S-curves. If you were to graph a parabola on your calculator, don't draw this on your notes, but if you guys like ever look at a parabola on your calculator, it looks like that. It's like real nice and skinny. But a lot of people, when they draw parabolas fast, they kind of go like that. Have you noticed that at all? Similar with the cubic graphs, if you look at your calculator, it's going to be like real nice like this. But when people draw them fast, they kind of draw them like that, and they make that middle part like over-exaggerated, kind of like how we over-exaggerate the U when we draw a parabola. So that's the thing to remember about a cubic, is it almost looks like it's straight up and down, but there is like this curve that happens in the middle. So that's a good thing to remember. All right, so we're going to go ahead and do an example problem for this. So we're going to do y equals -x minus 1 to the 3rd plus 4. And we're going to graph it, and then we're going to find each of the different characteristics for it. So for us to graph it, we're going to do our chart, and I'm just going to write down the points. I don't want there to be confusion on this. I do not expect you to memorize these tables. Please do not memorize them. If you're ever drawing a graph for this and you have to do the chart, instead of memorizing the points, just do this to start with, kind of figure out what the most simple version of the graph is, and then plug in -2 to +2, and then you have all your points for your chart. You do not have to memorize those. It's not effective for you guys to like waste your time doing that if they're so easy to find. All right, so there's the start. Wait, be careful. So, what do we do for that first transformation? I don't think it was. You sharpened your pencil and I thought it was fine. Yeah, you're good. You're good. What's the first transformation you guys can see? Reflect over x, and how do we do that? Keep the x the same. What happens to the y value? You multiply it by -1. Yeah, we just want to change the sign of the y coordinate so that becomes a positive y, or a +8, a +1. 0 is going to stay the same. The +1 is going to become -1, and the +8 is going to become -8. And these are your notes, so if you need to like write a note to yourself to remember how to do that, that's not a bad thing. So I'm going to put reflect over x, and then I'm going to put y times -1. That's what I did. Okay. What's the next transformation you guys can see? To the right 1. So how do we go right 1? Add 1 to the x. So -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. And then what's our last transformation? Up 4. So 8 plus 4 is 12. 1 plus 4 is 0 plus 4 is 4. -1 plus 4 is 3. And then -8 plus 4 is -4. Okay. So this one is going to be less awesome to draw since it goes all the way up to 12. And we're going to graph the point -1, 12, and 0, 5, and 1, 4, 2, 3, and then 3, -4. So if you guys can see this one, the parabola shape goes up towards the left side and then down towards the right side. So we've got our U shape right here, and then our U shape right there. So for our transformations, we have reflect over x, right 1, and up 4. And this graph does not have a vertex. Does anyone remember what vertex means?
Max.
It is a max or a min. Anyone remember what the actual definition of a vertex is? Yeah, it's the point where you switch from increasing to decreasing. We often thought of the vertex as like the middle of the graph. So we have that. We have a middle of a graph, but we don't have a vertex. It doesn't switch from increasing to decreasing.
Excuse this interruption, Northern High School. I have 2 quick announcements.
So we don't have what we're going to call a vertex because we don't have a point in this graph where it switches. Oh, so we don't have a vertex. We don't have a point where it switches from increasing to decreasing, but we do have a center point or like a middle point. And I usually call that the locator point because it's the middle of the graph and it shows up in the equation. Does anyone know what the locator point is on this one? You find it the same way you used to find the vertex. Yeah, it's +1, +4. So it comes from the equation, +1, +4. So that's the middle point on a cubic graph. And then we want to find things like domain and range. Is there any limitation to x values that you could plug in and subtract 1 from? Are there numbers you just can't subtract 1 from? No. Are there numbers that you're not supposed to multiply by itself 3 times? Because that's what cube means. You're multiplying by itself 3 times. Is there any limit to numbers that we can do that with? No, you can always do that. So what should I put for domain if there's no reason to limit the x's I can plug in? All reals. I can plug in any single x that I can think of.
What kind of graphs have all real?
Graphs that have all real for range are going to be graphs like this one, for instance. So when you have all reals for the range, it means that every single y value is being touched by the graph. So if you look at this picture right here, I can see that all these positive y values are being touched. And I can see there's an arrow that goes up. So that means that every single positive y value I can think of is always going to be there. And then there's an arrow going down that tells me that every single negative y value is also going to be there. And I can see that my graph didn't skip anything. So, yeah, so the range for this one is all real numbers as well. Yeah. And that's different because the other ones we looked at, it did have some skipped y values. So I think this might be the first graph we've looked at that doesn't skip anything. How about increasing and decreasing? What do you guys notice about this graph? We can draw like a little sketch of it. We got our little stick figure guy. Yeah, it only decreases, and it messes with students because they think like it's slanted like this and then it slants a little bit differently. It just means that it's decreasing like super fast and then it decreases like a little bit less fast and then it decreases fast again, but it's decreasing the entire time. Like if you were sliding down this, it'd be like downhill the entire way. So we're going to say increasing is none. And then what's the x value at a left arrow? And what is the x value at a right arrow? And so what's our decreasing interval? Perfect. What should we put for max or min? None. There aren't any. So, yeah. A max, yes. So if you look back at this picture, that would have been increasing the entire way. Yeah, yes. Mm-hmm. Yeah.
So it doesn't matter that -112 is the first point?
Mm-hmm. Nope. So maxes and mins actually, a max has to happen where you switch from increasing to decreasing. So a max has to look like a mountaintop. And a min has to look like a valley. So here we don't have that happening. We don't have that switch happening. We do have points on the graph that are higher than other points on the graph, so that's happening. But they're not considered a max unless they are look like a mountaintop. We don't have that. All right, so we've got those. And then what is the last stuff that we typically find? Yeah, x and y intercept. And those are calculator problems, so let's go ahead and plug this in on our calculator and then make sure that we can find.
Are these only going to have one x-intercept?
Yes, exactly right, yeah. We're only going to have one x-intercept because the graph can only cross at one time for
I like
this.
these better than parabolas.
Yeah, because less work, a little bit less work, yeah. All right, so I've got negative x minus 1 to the third plus 4. Yeah.
My graph showed up like the slant.
Did you miss your exponent of 3? Outside your parentheses? So x minus 1 to the third. How do we find the x-intercept?
Like normal.
So we do second trace number 2, and then we're going to do left bound and right bound. So my left bound is going to be a little bit above the x-intercept, and my right bound is going to be a little bit below. So our x-intercept is 2.6. And then how do we find the y-intercept?
Same way.
So second trace number 1, plug in 0. So 0, 5. Okay. So are we seeing how similar this is to what we've done in the past? Now, in the past days, I let you guys take like an entire day to work over one type of graph. Today, we're going to do 3 types of graphs in one day. So we're going to do square root, which you guys had in your video last night. Cubic is what we are doing right now. And then we're also going to do cube roots. All right. I'm going to flip my paper over because I like it to be organized. So we're going to do all 3 of these on one day, and that's because it's so repetitive that the idea is at this point you should understand it well enough that you can kind of apply the ideas to different situations. Are you guys feeling like you can do that? The graphs look a little differently. So the last graph is y equals the cube root of x. And we're going to start it just like the other ones. Hey. All right, so what x values are we going to plug in? Yeah, the same. We're going to plug in -2, -1, 0, 1, 2. Okay. Now this one, since we're doing a cube root, to get to that on your calculator, you hit the math button, and you're doing number 4. Now, number 5 is to be used for any other type of root. You can do 5th roots and 6th roots and 7th roots and 8th roots and 9th roots, any type of root you want. They put an X there, so if you're going to use option number 5, before you go to this, you have to tell it what number root you want. So if I wanted to do like a 10th root, I'd have to do 10, type in 10 first, and then hit the math button and go down to number 5. And my calculator would put the 10 in there and do a 10th root for me. Okay, so we don't need to use that today. I just wanted you guys to know what that one means with the X in it. So we're going to go ahead and use third root, and I'm going to do third root of -2. And that gives me -1.3. And then the cube root of -1 is -1. And the cube root of 0 is 0. And the cube root of 1 is 1. And the cube root of 2 is 1.3. Okay. And for this one, our example problem is going to be y equals 2 times the cube root of, did we go right or left last time? Right. So we'll do x plus 4 minus 1. So that's the example we'll do this time.
Is the -1 outside the thing?
Yes. So here we don't have parentheses, but the root sign kind of acts like parentheses. So this is your inside, that's your outside. All right, and before we go too far with the example, let's go ahead and draw a sketch of the parent function. Do you guys know what I mean by parent function when I say that?
It's almost like the original.
Yeah, it's like the original. So it's the one before it has any changes with it. So we've got the point -2, -1.3, -1, -1, 0, 0, 1, 1, and then 2, 1.3. And this, depending on how much of a perfectionist you are and like how good you are at like sketching graphs, you might not be able to tell, but those are not actually in a straight line. Does anyone know what this looks like?
They kind of like.
It's like the S curve, so it's like the last one we did, just flipped on its side. So this is kind of like a parabola going this way, and this one's kind of like half a parabola going that way. So that's what a cube root curve looks like. It's just the flipped version of a cubic. Okay. So we're going to do the chart. The reason I made you guys... We good back there? Are you okay?
I almost died.
Yeah.
In class.
You look like you just had a heart attack.
I do.
The reason we draw the chart is not because I'm trying to torture you. It's because anytime you ever see a graph, I want you to feel fully confident that you can graph literally anything and that you understand how the transformations work. That's the goal of it. And this way, if somebody asks you, like, what does a stretch of 2 do to the points of a graph, you're going to say, you're going to take all the y coordinates and multiply them by 2. You guys should all know that. So I promise you I'm doing this for your benefit, not to drive you crazy. Although it might feel like I'm doing it to drive you crazy. Apologies. All right, so the first transformation you can see is what? Stretch of 2. So the x coordinates are going to stay the same, right? And then my y coordinates are going to multiply by 2. And you don't have to like go back to any of them except for the one with the decimal. We rounded it so much we don't want to use a number that's quite that rounded to start with. And I'm going to show you why. Because if you take the square root of -2 and multiply it by 2, you actually get -2.5 instead of -2.6. Makes a little bit of a difference, but it's enough that we'll go ahead and use the actual number that we should have gotten if we didn't round. And then the rest of them we can just multiply by 2. So -1 times 2 is -2. 0 times 2 is 0. 1 times 2 is 2. And then if we did the positive version of that decimal times 2, then we would get positive 2.5.
Is there ever like a type of graph where if you put in like a negative and a positive, you get different answers?
Well, that kind of happens on the square root graph, because when you typed in negatives on the square root graph, you got errors. So that was 2 different things. I mean, it kind of happens here, but it was just the positive and the negative version of something. It shouldn't be, you shouldn't get 2 different answers until you get to the point like this where you're starting to use other numbers too. Yeah. All right, and then what's our next transformation? Left 4, so we can do that. We're just going to subtract 4 from all the x coordinates, right? So -6, -5, -4, -3, -2. What I've noticed is when students get these wrong, it's usually because they like mentally checked out while they were doing it. Like they just stopped thinking about their numbers and their numbers stopped making sense. So I think as long as you pay attention while you're doing it, most of you guys are pretty good at this. What's our last transformation? Down 1. So -3.5, -3, -1, 1, 1.5. And then we can go ahead and graph it. So we've got -6, -3.5, -5, -3, -4, -1, -3, +1, -2, +1.5. Can you guys tell what that middle point is on this one?
Yeah, it's the negative.
So you can look at the equation to find it, right?
Oh, yeah.
Yeah, -4, -1. Yeah. -4, -1. So our middle point, or our locator point. Some people, when they start to get sloppy with these, they'll be like, okay, my middle point is at -4, -1. And so they'll draw a little sketch. They'll go left 4, down 1, and then they'll be like, whoop, whoop, there's my graph. It's a sloppy graph, but it's essentially the same thing, right? So that's where the locator points kind of come in handy, is they help you do like a really, really quick sketch if that's all you need. How about domain? You got to think about x values that we're allowed to plug in. Yeah, if you look at your table, so if you think about square roots, regular square roots, you can't plug in negatives, right? We found that on the video last night. We got error messages. But here we were able to plug in negative values, no problem. So for this, negative numbers are good, positive numbers are good.
So rails.
Or all rails, you could say it that way if that's your preference. Yep. And then for the range, if you look, we just want to see, once you do use those x values, what are the y values that spit out as an answer? So what y values do you guys see on that picture? I can see everything between like -3 and +2, right? All those are definitely hit. Those are on the graph. And then I've got an arrow going up. So what do I know about y values that are bigger than +2? It's, yeah, all of them are going to get used. And what about y values that are less than -3? There's an arrow going down. So they're all going to get used. So what does that mean? The infinity, so it's going to be negative infinity to positive infinity. So I can see an arrow going down and an arrow going up, and there's no gaps in between. So nothing got skipped. We got everything being used. All right, how about increasing and decreasing?
Excuse me,
Yep,
could you send Madison Williams to sign out?
yes.
Thank you.
So for this, we'll go ahead and label our little stick figure dude. And what do you guys notice about the little stick figure? He's going up. Yeah, he's going up slowly and then quickly and then slowly, but he's going up the entire time. So that's why Leah was saying that decreasing answer is none. And then what are our two x values on either end? Yeah, negative infinity over there, positive infinity over there. So we're going to say he's increasing from negative to positive infinity. What about for max and min? If we look for those, are we going to find any?
No.
Nope. We got no mountaintops and no valleys, so no max, no min. And then how about the x-intercept and y-intercept? Yep, we gotta graph it. Is there ever going to be a point on these where we would not have an x-intercept? But look at what happens if it's above it, it's got an arrow.
No.
It would hit it eventually, right? It just might hit it off the screen. So these are always going to have one x-intercept and one y-intercept every single time. So if it's not happening on the screen, you got to make your screen bigger so you can see it. Okay, so we got 2, and then I'm going to hit the math button, get my third root in there. There we go. So third root of x plus 4, and a minus 1 on the end. You guys want to see a trick so you don't have to scroll? Anybody want to see a trick?
Yeah.
I hate scrolling left and right to do left and right bound. So when I look at this, I can see that my x-intercept is somewhere between -10 and 0. Would you agree with that? Somewhere on the left side. So I'm going to do second trace to find my x-intercept like normal. Look at number 2. And then for my left bound, I'm going to type in -10 and press enter. And for my right bound, I'm going to type in 0 and press enter. My calculator is going to look for it between -10 and 0, and it's going to find it. I didn't have to scroll. Nobody? You don't like that trick? Because I love that trick. I do that trick all the time. You like that? If I show students how to do that at first, they get all confused. So, all right. So our x-intercept is -3.9. Do you guys see how on the picture it looks like the graph has a gap? Does it have a gap? No, we know it doesn't. The reason your calculator draws it with a gap is because for that little bit in time right here in the middle, the graph appears to go completely vertical. Are we allowed to have graphs that are completely vertical? Do you guys remember the vertical line test? Anyone do that with their pencil, the vertical line test? If your curve does not pass the vertical line test, it's a function. When you hit the y equals button, you are only graphing functions. So your calculator doesn't like any part of a curve that appears to go vertical. It kind of just blanks that part out. So there is no gap on there. This is a technological kind of glitch in your calculator where you just have to be smarter than your calculator and you have to know even though it looks like something's missing, it's not. It's actually there. And if you were to like trace the graph, like have your little cursor thing just kind of go along the graph, it would have a value for every single thing. It wouldn't skip any values. They'd actually be there. So just watch out for that. It's really easy for students to think that there's gaps there when there's not. All right, how do we find the y-intercept?
X equals 0.
Yeah, number 1, plug in 0, and we get 2.2.